So we're going to talk about the nonlinear systems today. Things about types of models, and that you can read in chapter 2 a little bit further. Big distinction between parametric and non-parametric models. For instance, a parametric model was the filter that we looked at, where you know what the component is, the R and the C, and then the R and the C are the parameters, and that would be a parametric model. The non-parametric version of that model would be a black box in which you know what the unit impulse is, and that would be non-parametric. That's the non-parametric version of the same thing. Funny enough, you could say that a non-parametric model contains more parameters than a parametric one, because if you have to parameterize the whole unit impulse, that's a lot of parameters, of course, in your model. Sometimes you also get a somewhat different application. For instance, the well-known Hodgkin-Huxley equations, well known for the people in neuroscience, is based on an equivalent circuit with R's and C's and conductances and membrane capacitance. It's actually a parametric model, but the parametric model is basically a model of the membrane, so it can be more or less an indirect model of what is going on. At the time that, by the way, Hodgkin-Huxley defined their model, it was just purely a heuristic way of approaching the membrane, because they didn't really know that there were ion channels. Ion channels were discovered really much later. So they postulated in 52 and 53 that you had these conductances across the membrane, but nobody had ever had any evidence that things like that would exist. Then another distinction, and I think we have mentioned that before, is that you can have static and dynamic models. And if you have a static linear system, we said, well, it just means that you get some typical equation that describes how the input and the output are related. If you have a static nonlinear system, it's basically the same thing. You do not have any memory. So there is no memory available. And if you call the output y, then basically the output y depends precisely on the input x. If you have a dynamic version, then there is memory. And then, of course, the current input at time t, but also with some delay, the past input is determining what's going on. So then you get this thing. And you recall from the linear system that we had to describe the output as the convolution of the unit impulse, the characterization of that system with the input. And then when we did that convolution, we could kind of compute what the output was. So let's give an example. For instance, if I have a static nonlinear system, it could look like this. Now I can have a constant. It's a nonlinear system. And this would be let's say a Taylor series that I truncated at the second order. So this would be a second order nonlinear system, static nonlinear system, described by a truncated Taylor series. Now let me give you an example. And this may look a little bit complicated at first, but you will see, you will get used to it. Basically the same thing. We have some kind of a constant, and then a term that looks pretty much like one that you have seen already. So again, this is a constant, and this term is a term you probably find somewhat familiar, isn't it? That's what we would call a convolution. So this is the first order term, just as this thing contains a first order term. And now we're going to add a second order term, and the second order term is not a big surprise. It's just a bit complicated to write it all down. Because instead of now convolving some characteristic function with one copy of the input, I do it with two copies of the input. See? So it's kind of a long expression, but in a way it's not unexpected, because if this copies a characteristic function of your system with one copy of the input, then the second order term is doing that with two copies. And you guessed it, the third order term is with three copies, and the fourth order term with four copies, etc., etc., etc. And this would be a dynamical system, so not static. It is a dynamical second order system. And where this is a Taylor series that was truncated, this actually is a Volterra series that's truncated. Volterra, named after the first one who came up with this, Vito Volterra, who lived the late 1800s, early 1900s. And let's try to make this system a little bit intuitive. And again, this system, of course, is this description is a non-parametric description, isn't it? It's like our filter, where we characterized our filter with the unit impulse. So it's kind of a non-parametric version. Sometimes it's helpful to kind of try to understand this by just taking an example with a parametric case, or a somewhat parametric case, so making the black box a little bit whiter. In this case, we're going to not do that entirely. We're going to do that later. We're going to go all the way. But right now, we are going to first simplify the system in a cascade. And so here I'm not going to completely parameterize it. We're going to say, well, let's kind of make a second order system by taking a first order one. So here is our first order system. And as you can see, this is a dynamical first order system, at least depending on age, of course. And now we are going to make this system nonlinear by cascading a static nonlinearity. And this whole system would be a cascade, where this is the linear component and this is the nonlinear component. So it's also sometimes called an LN system. It is a dynamical system, but the dynamics is completely in the linear component. That makes it a little tractable, a little better tractable. So we're just now applying our knowledge of linear systems here. And we know from that y is nothing else than the convolution of this unit impulse response of the system. Isn't it? We know that. And so since we now know what our nonlinearity is, we can write an expression for the overall output z. The overall output z is a naught plus a1 times y, which is h tau xt minus tau d tau, plus a2, and then this expression squared, isn't it? There you go. And I'm just, for convenience, because we get so many integrals here, I'm just leaving out the integration limits, but usually they are taken from minus infinity to infinity, but we could also take them from 0 to t, if we look at a causal system. But usually you will find them in the books as from minus to plus infinity. Well, let's first look at this one. If I'm going to rewrite this a little bit, I could take a1 over here. So I could rewrite this in such a way that I have my integral here and I have a1 there. And there you can see that if I substitute for this expression, if I substitute like h1 tau, then I already have two terms of my truncated Volterra series there. See, I have my constant, which I'm going to write now as h naught. I just rename them. I'm going to rename this thing h1 tau, and then basically my second term is also taken care of. I have that one. And now I'm going to rewrite this expression here. And I'm just going to write it all out, which is, in this case, it would be, well, let's kind of write it like this. And I'm just changing the dummy variable tau in tau 1 in the first factor and in tau 2 in the second factor. I mean, since it's an integral, I can use any dummy variable that I like. And I just rewrote this part now. The part in between brackets is now, instead of a quadratic expression, I just expanded it into expressions. And then I can, this part I can now write as a double integral. And you can now see that if I put in the constant a2 here also into the thing, then I can rewrite this part of the expression as h2 tau 1 tau 2. And then if you put it all together, you can see that I get this term again. So you see that it kind of makes sense to use a Volterra expression. You can already see that it makes sense because we know what convolution is. And so, well, if you have a second order system, it probably is a convolution with 2 copies instead of 1 copy. But if you then just take a specific example of a second order nonlinear system, you can see that indeed you can immediately converge to that type of expression. Now this expression is a little more general than this example, of course, but you can see that this specific example fits the general expression.
Mm-hmm. Question. So H2 of tau 1, tau 2,
mm-hmm.
Does that also take into account A2?
Yes, that's what I mentioned. I said, well, you have to take into account that you have to put in the constant there. But that doesn't really change the idea. Yeah, so if you want to, I can make it that would be the correct way of doing it. I know I said it, but I didn't write it down. Yeah. Yeah. Mm-hmm.
I don't quite understand why we went from tau to tau 1 and tau to second order.
Oh, okay. So basically, this is the integral in the square is basically 2 integrals. So that would be tau, 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 tau. Since this is the integration variable, I can use any variable for integration because it vanishes after integration, isn't it? Mm-hmm. And so I call this, just because it's convenient, tau 1 everywhere, and this tau 2 everywhere. But that allows me then...
Like, why can't you just call it plain tau everywhere?
Well, because I actually want to get this expression.
Oh, okay. So it was just to turn it into... Okay.
Right.
All right. But it's
That's the reason it's convenient.
actually different. All right.
No, it isn't. No, it isn't.
Okay.
Now, this is just another way of writing this thing. And this thing can be written in this way because in this example, we have a very special example of a second order system. Whereas this is a more generic way of saying it. So this is more generic, that's more special. Now let's make this system again static. Let me ask you, where is the dynamic component in this cascade? I actually said it a while ago, but the dynamics is here, isn't it? Because this is static, so the dynamics is here. So if I remove the dynamics, I can make this system static again. I can easily remove the dynamics by doing this. I'm changing the unit impulse response into the unit impulse response, which means now, in principle, my input is going to be my output, isn't it? If I give it a unit impulse, guess what? I'm going to get a unit impulse. In that case, I can in this equation, I can replace x, the input, everywhere by the unit impulse, isn't it? So let me do that. Here, it's going to be the unit impulse. Here, it's going to be the unit impulse. Here. 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 And there. Did I forget one? I don't think so, huh? So everywhere where I had x now, I basically now use a unit impulse. Oh, what did I do wrong? This is not what I want to do. I want to kind of keep this x. So I'm going to change them all back. That's what you get when you try to be efficient. What I should have replaced was not the input, but the function for L, isn't it? So I should have replaced H. So that's better. And we really like integrals with delta functions, isn't it? Because they evaluate so easily. So here, basically, nothing happens. This remains A naught. But here, basically, what I do get is, what does this integral evaluate to? If I apply the shifting property here, my outcome would be A1 xt, isn't it? So, and this just remains A naught. And if I apply the shifting property here twice, what do I get? I get A2, and then I get xt for this one, for the tau 1, and I get xt for this one, for the tau 2. So if I apply the shifting property twice here for this term, I get A2 xt squared. So lo and behold, if I make the system static again, I get my Taylor series back. See? A naught, A1 xt, A2 xt squared. That was my Taylor series that I initially used for my nonlinearity. And you can also see that there is a strong relationship between the Volterra series and the Taylor series, because the Taylor series basically give you the static version of the nonlinear systems, and Volterra basically is the dynamic. And if you make the dynamics go away, then this thing becomes the Taylor series again. So now it's actually maybe nice to generalize this result to show you the full Volterra series. And this is a figure in the book. It's figure 3.1. And here is the idea. This is what we looked at before we started talking about nonlinear systems. This is a linear system, linear time invariant system, and it's governed by convolution. This is an example of a second order nonlinear time invariant system, an NLTI. And you can see it is kind of a double convolution. It's convolving this h function with two copies of the input. And then here, and this will go away in a minute, you have a generalization of an NLTI filter. And you can see that the NLTI filter is considered to consist of linear and second order and higher order components. It has some input. Every component creates a convolution-like term. Of course, the first order one is a very simple convolution. The second and third order one are convolutions with multiple copies of the input. And depending on the order of your system, just like you have that in the Taylor series, depending on the order of your system, you basically have multiple components of this order, and then at the end you just add them all together. This is the plus sign here, and so your nonlinear system consists of the sum of all these different components. And this is the full Volterra series describing the dynamics of your nonlinear system. So just to make sure you understand this, I did not prove anything to you. I just made it kind of intuitively likely that higher order systems had needed multiple copies to get a convolution-like term. And when we looked at the second order system, I just used a very simple cascade to make it intuitive. Of course, it's not proof, but this is just to make it more or less intuitive that this is how we should be describing these systems. I'm going to leave this on and show you a couple of alternative notations. Because as you can see, even with the blackboard here, I get out of real estate really fast because you get lots and lots of terms. So you can actually use sometimes a little shorthand. You could, for instance, say, well, I'm going to write my output as and then I'm using this symbol, this X in the circle, to indicate convolution-like operation. And then I just go on until I'm done with my term. So in this case, I have written down a first and a second order term. Of course, if I wanted to have a constant, I would have had an H0 here as well, H0. Another way that it's often written down is like this. Can be practical too. Then you say, well, my output is some first order. In this case, you would call this an operator. It takes a function and turns it into another function. In the older literature, they would call this also functional. But to be honest, strictly speaking, nowadays functional is it would be an operation where you took a function and changed it into a value. In this case, we have a function xt, the input function, or a time series, and it gives you an output function. So from function to function, It's better to call it an operator. So this is a first order operator, and this would be a second order operator. And in this case, since this is a Volterra series, this is a first order Volterra operator, and this is a second order Volterra operator. Of course, this is nothing new or different, it's just a different notation. But this is I think this is quite an important figure. If you understand what's going on here, you basically understand how the Volterra series is kind of conceived. Clear? Good. So how do we characterize linear systems? A linear system is a system where there is always superposition and scaling. So that means that if this system is nonlinear, it should not obey these laws of superposition and scaling. Because if it did, it would be linear. So let's have a look at that, at these properties of scaling and superposition. Start with scaling. That's the easiest. So if I have an let's say I'm using a delta function as input. And let's say that I have a linear system. I had this situation, isn't it? And this is what I would get. And for the same, so this is an LTI system. Now let's kind of look at a second order system. And let's take a very simple one with only a second order term. So we only have this thing. So here I apply the shifting property once and I get HT. Here I apply the shifting property twice and I get H2 dt, isn't it? I replace 1t for tau 1 and 1t for tau 2. Now I'm going to scale this thing. Instead of giving this an input delta, I'm going to give it an input, write that down a little bit wider. I'm going to give it an input C times delta. And if I do that here, I basically get a C here. and a C there. So that means that if I increase my input with C in a linear system, my output is going to be multiplied by C. That's scaling, isn't it? So indeed, LTI is linear. We're happy. Here, on the contrast, if I do that, I get a C here, and I get a C there, and I get a C squared here. So here you see that the second order system indeed does not obey scaling. It actually squares the scale. So if you multiply the input with C, the output is going to be multiplied by C squared, not C. So that makes the second order system nonlinear. Huh? Now a related question. I said, and we have said that often, if I know the unit impulse response of a linear system, I basically know the system, isn't it? Is that true for a nonlinear system as well? Why? So you said yes, because H2 kind of creates an insight into the system. Hannah was kind of nodding no, and why did you say no?
You don't know how you get H, but you don't know how it scales or how it responds to other values. Because the reason unit impulse tells you everything is that you can construct an input algorithm.
Mm-hmm.
That's the reason again, but you don't have that. You can't construct an input.
It's not entirely, it's true, but it's not entirely the answer I was looking for. Just look at this thing. This is what I need to construct my output. See? And what I get with the unit impulse is the diagonal of that function. See? So I get only the diagonal here, and I need the whole function. And so for that reason, the unit impulse response in a second order system is not sufficient to create an output from any arbitrary input. Whereas for a linear system it is, because if I know H2T, I know everything there is to know, because that's all I need to know. That was scaling. A little bit more involved, but nonetheless interesting. And as we will see in a bit too, very useful, is looking into what happens with superposition. We already know the system is nonlinear because it doesn't obey scaling. And as soon as one of the things is not obeyed, you know it's nonlinear. But in this case, I can tell you that the superposition is also violated. Let's take an input x that consists of x1 plus x2 to a second order system. And we will often use a second order system again because my blackboard here is limited, and usually the principles as they are appearing in second order systems is really appropriate to understand what's going on. So in that case I would have this. There's my double integral. Here is my H2 function. And now I'm gonna have to I kind of wrote this between curly brackets because that's the only part I'm going to continue with. I'm not going to repeat everything. So the part between curly brackets, I can now write as see? So I just change x for x1 plus x2 with a delay tau 1. And I change this x for x1 plus x2 with delay tau 2. Now if I'm going to expand this stuff, you can see I will get 1, 2, 3, 4 terms, isn't it? When I expand the thing between the curly brackets. So let's look at these 4 terms separately. Term 1. Term 1, and I'm going to write out the whole thing again. It's going to be H2 So that takes care of this multiplication, isn't it? Both x1s. That'll give me that first term. Let's also, just to keep it easy, let's kind of take this term and call that the second one. That's going to be my second term. And as usually when you write these things up, it's not a bad idea to wait a second and look at this and say, well, what actually does this represent? That is correct. Check it with me. This is the H2 function convolved with x1 at 2 delays. So that is basically the output of the system to input x1. And for the same reason, this is the output of the system to input x2. So you could, in short note, you could write it like this. If you wanted to use the shorthand notation that we used a while ago, you could say, well, this is basically H2 of x1, and this is actually H2 of x2. Isn't it? Now, if we think about this a little bit further, if this were a linear system, this would be it, isn't it? Because the total response would be the sum of the response to x1 and the response to x2 separately together would be the total response. But yeah, this system is not linear. So here we actually get also, in principle, we get this cross term of x1 with x2. That would be, and the other one would be this cross term, x2 with x1. So these cross terms are as follows. last one. And you could say that these two together, because the total response of the system is the sum of these four terms, isn't it? If I add them all up, I have the sum of the system. So the terms 3 and 4 are basically the deviation from the linear response. Because 1 and 2, 1 plus 2 represent the linear component of the response, and 3 plus 4 is the deviation from that. Something that, again, I'm not going to prove to you right now, but you will see in a little bit that it's actually pretty intuitive, that H2 is actually a function that is symmetrical around the diagonal. And the reason, as you may see, I don't think we'll get there this lecture, but the reason, as you may see pretty soon, is that, of course, when you have, let's say, a delta function with delay tau 1 and a delta function with delay tau 2, the system doesn't know which is which. So I can interchange them, and that could make it quite intuitive that this function H2 is symmetrical around the diagonal. And if we do that, if we accept that, then I can do again the same thing, Sophia. I can, since these are just dummy variables, I can change tau 1 into tau 2 and tau 2 into tau 1. Doesn't really matter. And then the expression for 3 and 4 becomes identical. And then I can say that in principle this thing becomes 2 times H2 x1 x2. And so now if I want to summarize our result for superposition, I can use this shorthand notation. It's a little friendlier. I was going to look at the output to input x, and x consisted of x1 and x2. And what we just found is that that is nothing else than H2 of x1, the first term, plus H2 of x2, the second term, plus 2 times H2 of x1 and x2, which is the third and the fourth term. So this all summarizes our result. And you can see that the first 2 terms, again, represent superposition, and the third term, basically it's the third and the fourth term, but they are the same, so they converge into a single one, is the deviation from this superposition. So if you are, for instance, if you are a neuroscientist and you're looking at 2 neurons that are coupled, and you hit the presynaptic neuron and you look at the postsynaptic effect, and a little bit later you do that again, and you wait long enough, then you get the same response, because then the neuron has forgotten that it has been stimulated. But if you start to do this closer and closer together, you will start to see some interaction, because the neuron is basically still working on its response to the first stimulus, and then the second stimulus is already happening. If now the neuron was linear, you would find that your result would be just a superposition of the two separate ones. But if the neuron is nonlinear, you will see that the postsynaptic response that you get as a result is not going to be entirely the same as the sum of the two independent ones. And what we are seeing here is that if you are really smart about that, the difference of the deviation from that superposition is exactly, if you had a second order system, is exactly this. So you can actually use this to your advantage and say, well, let's assume that this is a second order system. Then you can use that deviation from superposition to say something about that system. That's the idea. So let's test that. That's again something, if you then want to test that, you like to go to a system that you know a little bit better. So for instance, a parametric system. And what we will use for this purpose is the following system. That's a system. It's shown in figure 32A. And it's kind of a cascade again. Consisting of a linear component, and that linear component may look a little bit familiar, because this was our low-pass filter. But this is a system that is linear. It adds dynamics. And then again, we take a nonlinear component that is, let's put it this way, that's easier. No. Yeah, in the example, apparently I haven't used this. I did this, so I'll keep it to the example as it is in the book. I will call this thing FT then. And this is, in good English, a squarer, something that squares its input. And this as a whole, again, is the cascade. This is the nonlinear system. Now, we basically now know this system. We know what's going on. We know what the dynamic component is, and we know what the static component is, because this again is static. There is no dynamics involved in this. The dynamics is all sitting here. I can easily find out what H2 is actually. And you see there is no zeroth order component here. There is no first order component. There's only one component here. It's a second order component. So in that case, there is only an H2. and that's nothing else than so we now know what this H2 function is for this particular example system. Now just keep in mind this, I'm going to erase this part on the right part of the blackboard. But keep in mind this, that if you have the input to two independent inputs and you compare it to the sum, then you get a deviation from linearity. And that deviation from linearity is something we can start using. And that is exactly the strategy that we are going to follow to characterize this system. Because what we are now going to do is we are going to pretend that we don't know this system. So we are going to, although we know what's going on in this system, we are pretending that this system is a black box. And the only thing that we know about this system is that it is a second order system. And our assignment is to characterize H2. That's the goal. So how are we going to accomplish that? Well, we're going to follow the following steps. So for step one is that we pretend we don't know this system. And on pages 48 and 49, you can see what we are going to do. First thing is we're going to use pairs of deltas at time step 1 and time 1 and time 2. And to kind of relate it to our previous example, the deltas are going to be called x1 and x2. Then, as a next step, we will determine y1 and y2 as responses to the two delta functions with the timing t1 and t2. But in step 2, we will do that individually. So now we know what is the response to delta function at time 1 and what it is to a delta function at time 2. As a third step, you already guessed it, we will determine y as the response to x1 plus x2. So now we're going to give the system two delta functions, just as the neuroscientist who stimulates the neuron twice in a sequence. So first he he determined, oh, I have one action potential at T1, another action potential at T2, and now I'm going to have the action potentials in series. This, by the way, is the reason that I mentioned to you that it's very likely, or it is kind of intuitive, that H2 has to be symmetric around the diagonal, because the system really doesn't know which one is which here. They're two delta functions. So now we, as a fourth step, we can take advantage of our knowledge, and we say that, well, H2 to the delta function pair is the total response minus the delta function minus, and I have to kind of continue here, the delta function at T2. And this whole expression has to be divided by 2, isn't it? So I'm just using what we found is that the derivation or the deviation from linearity was 2 times this this expression, and as you can see, yt minus the response to the one and response to the other divided by 2 is indeed, of course, going to generate this expression. We are now getting close, but we are not there yet. Step number 5. We are going to use equation 311F, which is the one that we discussed a little bit earlier about how you can define just the operator itself. So now I'm going to write it out full again. I have to kind of continue here again. So now I wrote down my operator again in full, and one signal was t minus t1, and the other signal was t minus t2. I have to give him a delay tau 1 and tau 2. I could have flipped that, of course, but it's easier to keep 1 and 1 here and 2 and 2 there. It's just a little easier to read, and then integrate it. So that's my step number 5. And if I integrate this, using the sifting property, I get this, isn't it? And now I'm there, because now as a final step, I am going to substitute or set tau 1 equal to t minus t1 and tau 2 equal to t minus t2. And then you realize that for that reason, if I solve this for t, that tau 1 plus t1 is equal to tau 2 plus t2. Or I could also write this as tau 2 is equal to tau 1 plus t1 minus t2. And so when I combine this approach, I'm going to find H2 t minus t1 t minus t2, and just to make it a little bit easier, I'm going to use this this substitution. And what I now get is the following. By doing this, if this is tau 1 and this is tau 2, I basically, every time that I provide a pair of unit impulses with delays t1 and t2, I get a diagonal where the intercept, as you can see, is t1 minus t2. Because t tau is equal to t1, so that is a 45-degree line, so parallel to the diagonal. And the intercept is t1 minus t2. So what I get by giving it a pair of every time that I proceed, that I use this procedure, I will get a slice through this H2 function. And that is something that we will do in practice in MATLAB next time. So you will see, actually, if you want to look at that in advance, it is program 3_1. That is exactly what that program is doing. It takes the system as we defined it, so the filter plus the squarer, and then it computes H2 and said, okay, this is what H2 is supposed to be. Now we are going to give the system pairs of pulses, and then we use these 6 steps to every time that we do that to create the diagonal for this H2 function, and then we repeat that a number of times. And of course, since this thing is symmetrical around the diagonal, we only have to do that in this direction. We don't, once we have let's say filled up this part, we basically don't have to do anything else because that's symmetrical relative to the other part. Your homework. Is 3.1 and 3.2. And pay attention, it's 3.1 and 3.2 from the second part, so you should go all the way to the end in your exercises. Any questions before we stop? And again, since things are getting really intense, it's a good idea to read a little bit in advance. Okay, then we're done.